Hello and welcome back to Calculus 3. Alright, so 14.2 line integrals part 2. We are going to work one or more of these basic problems and then work our way to circulation. And so we said that we have the vector field version of the line integral, and I want to take a look at one more example so we know what's going on. One of the applications of this line integral would be the work integral. Would you agree that wind would push something along the line? A stronger wind could push a car, could push a tree or a house. The smaller wind, you know, it's going to push a leaf or whatever. So there is a force that it's applied over area, and clearly, you know, if something is aerodynamic, it's not going to cut that much through the wind, but, you know, boxier things are going to catch a lot of wind. You probably felt as you drive on a highway or something, when you had a huge crosswind, like a very strong crosswind, it kind of sways the car a little bit. If you have a taller vehicle, now I have to look at Ryan over there because he's like, yeah, right. So the work integral will be another example of what we have, and the force could be, you know, given to us by. So let's take a look at one of the applications. Let's write it in red. So work, right? W is equal to the integral on the curve C of f dotted with the tangent vector ds, which we can write as integral a to b of the vector field f, which is what provides the force, times the r prime of t dt. So this is, r prime is also a vector. So this would be the formula for work, and I would like to just go and review how to work on these integrals using an example. So we have, let's say, problem 41 as unusual. F is given as y comma x, so we have our vector field, and then we have our curve C, which is a parabola y equals to 2x squared, but it's from 0, 0 to 2, 8. Now, it's important to have these endpoints because that gives you t, which is going to give you a and b. So we have to parametricize this, and once we parametricize this, we also have to use the... So now let's first do our parametrization. So for parametrization, we start with, we can assign x to be t, and then y would be 2t squared. So this is the easiest way to parametricize something, by just assigning x to be equal to t. Is this the only way? Obviously not. We have many other ways in which we could parametricize this, but, you know, this one would work. And now if you take a look at your t, t will simply be between 0 and 2, because this is x and this is x1 and x2, right? Those are the x1 and x2. And since x is equal to t, then t goes from... Now you can check if the y component fits as well. It has to. Plug in 0 for t, you get 0. Wait, did I write something wrong? Yep, so 0 is 0, and when I plug in 2, 4, 8. Great. Everything is good. So we have our parametric equation from where we know we can write it as r of t is the vector t 2t squared, and then from there we need our r prime, which would be 1 and 4t. We have our vector field f. We have our r prime now, and all I need to do is to plug all of this in. So what's the work? Work is given as the integral 0 to 2. Now my vector field f is going to be, I have a y is given as 2t squared, comma x is given as t. We need to dot that with 1 4t dt. Now we do the dot product, and then we'll integrate. So for the dot product, I have 1 times 2t squared plus 4t squared dt, which is integral 0 to 2 of 6t squared dt. And finally, that is t cubed, so 2t cubed from 0 to 2, which is 16. Did they give us any units? No, they didn't give us any units, so whatever, Newton meters or joules. Okay, joules or what else do we have? Feet, foot pound, whatever units you put. So if you remember, the force over here is your vector field. Vector field has the F and the G, right? And these are your X and the Y. So they get plugged in up there, and we have the problem solved. So last time I mentioned that we have to talk about two other phenomena, and those would be the circulation and the flux of a vector field. Each measures a different thing, so let's take a look at what they mean and how to find them. So we'll start with circulation. So for circulation, we have the definition, and it says let F be a vector field on a region D of R3, and let C be a closed, smooth, oriented curve in D. The circulation of F, which is a vector field, on C is the integral over C F dot T ds, where T is the unit vector, I mean unit tangent vector, so is the unit vector tangent to C, consistent with the orientation. Huh? Right? What? What is this stuff? Well, I need you to think of the wind, and then just a regular wind, you know, the one that you feel as it blows, let's say, due north or whatever. And then think of a tornado. Are they both winds? And what's different about them, right? They both move particles in the air. They both move mass of air. They're both vector fields, but they're different. Because the wind that just blows straight, right, is the wind that pushes forward and has no spin to it. Where a tornado has a spin to it. We can measure that motion, that behavior, using these things. For instance, if I have a straight path in some vector field, there's not going to be any circulation across. If I have, sorry, not a straight path, circular path. Well, now I have to use different color. There we go. And if you take a look, you have a tangent over here and another tangent on this side, and they're not making this spin because they're both pushing the same. However, if I have circular path C and then I have some kind of vector field that maybe looks like that. Well, in this case, you see that it's trying to spin it counterclockwise? So we can measure this by measuring what we call circulation. Circle, right? It's trying to circulate it, to rotate it. Now let's take two extreme examples and show exactly what needs to be seen and explained in these examples. One of two basic vector fields would be the radial vector field and rotational vector field. So radial vector field is going to be given to us as just simply x and y. This is the one that, you know, the kids draw as a sun, like that. That's the radial field. It shines the energy outward. What are you expecting circulation to be for something like that? Zero. There's no spin there. Let's prove it. So this on the unit circle. Now unit circle, we know that the unit circle can be represented as vector r is equal to cosine t sine t, where t is entire circle 0 to 2 pi. So is circle closed? Yes. Is it smooth? Yes. Is it oriented? Well, we put the cosine first, so counterclockwise. Yes. It passes all of those marks, right? And then we have, now we just need to solve this, right? So I have my integrals. You know what? Put this. Why? Because your curve C has all of the specs. It's smooth, it's closed, it's oriented. That just means when you put that little circle around the integral sign in the middle, That just means that the curve C has all the specs. Oriented, smooth. Smooth means differentiable, no spikes, no sharp turns. Like, absolute value has that spike, and so on. So, smooth curve means differentiable everywhere, has those tangent line derivatives everywhere, and then we have and it's closed, right? It's a full circle. So when you see that, unfortunately, we're not going to get into the surface integrals and some of the other stuff where you see this and you see that. It just means the region it's such. All right, so what do I have? F dot T ds is going to be integral a to b f dotted with r prime dt. Now let's write our r prime, underneath r prime. That's negative sine t cosine t. Great. Plug everything in, integral 0 to 2 pi. F is given as x comma y, so that's going to be cosine t sine t. X is cosine, and yes, good. And then we have dot that with negative sine t cosine t, everything dt. And when you do the dot product, you have negative sine cosine, positive sine cosine, so this is integral of 0 dt, which is 0. So we have our 0 for this one. So that was radial vector field. Now we're going to do rotational. Are we expecting 0 again for rotational for circulation? No, right? We are expecting a value. So now for rotational vector field, we have that our vector field F, let's do F first, is going to be negative yx. That's the standard one. Again, unit circle, so curve C is going to be the unit circle, cosine t sine t, and our t is between 0 and 2 pi again. So now, when we run the circulation, again, we are going to have the dot product. So integral on the closed curve of the negative y, that's going to be negative sine t, comma x is the cosine t, dotted with the derivative of cosine t is negative sine t, derivative of sine t is cosine t, dt, and from here I hope you see it's 2 pi. Oh, I forgot to put the limits. Limits are 0 to 2 pi. Because sine, what's a sine? Negative sine times negative sine. Sine squared. And cosine times cosine? Sine squared plus cosine squared is 1. Integral of 1 is t. Plug in 2 pi minus 0, right? So 2 pi minus 0 is 2 pi. So there it is. Kind of gets interesting that you get to Calc 3 and you can just look at it and know. It's like, oh yeah, this is 2 pi. It's the dot product and then trig identity and then fundamental theorem of calculus part 1. And then we have 2 pi. Done with circulation, flux. Maybe it's worthwhile to just take a look a little bit at the beautiful pictures they give you in the book. Ta-da! Look at that. Circulation. They give you the vector field oriented curve. You see it's counterclockwise oriented curve. This is in 3D space. And so this on the tilted ellipse, right? Orbit of a planet, right? not all planets are in plane, right? Some orbits are tilted. So there we go, right? And you see the rotation. You see which way it's trying to spin.
So for the last one, what exactly does the value of Q5 tell us?
How much? It's quantification.
How much it's rotating? Okay.
How much stuff it's trying to push out. Now, flux. Flux is the amount of stuff that you are trying to push through the area. So now we're going to talk about the normal. See, when you take a look at the fan, too bad we're not in the other room now. We don't have a fan in this room. Think of the fan. You have that blade which sits in a plane, right? And you have the area of the fan's face. When you turn the fan on, the entire face of the fan is producing the wind, which is the vector field that it pushes, right? The bigger the fan, more air is pushed. Smaller the fan, less air is pushed, right? So the flux is the amount of stuff that goes as a vector field through the area. Now, it will always go perpendicular to the surface through which is coming out from. So the fan, the blades, are generating the wind, the push. And you know that if this is the fan, if you stand next to it, you feel no effect. If you stand behind it, you feel no effect. Below, above, no matter. Only if the fan is facing you, you are feeling the vector field it creates, which is the wind. Vector field, flow of the liquid, and so on. Cross-sectional area of the blood vessel, right? It's going to have blood going. So you make a cross-sectional area. You're looking at the, let's say, perfect circle, obviously much smaller, and then all of the blood that it's pushing through, right? It's going to be infinitely many vectors. At each molecule of blood, it's going to have additional, it's going to have a little vector that is pushing the blood that way, right? So the area is filled with blood, and all of the stuff that is coming out, right, is the flux that measures. What do we have for energy? Wow, electric field, magnetic field, right? They all emerge from certain areas. You want to make electrical motor, right? Well, you better know your rotational magnetic field. Otherwise, nothing is going to work. You are supposed to create a spin. You have the river push on the pedals, right? That will create the spin on the axle. That brings it to the rotor of the generator. Rotor spins, creates the magnetic field, which creates electrical energy. Motor is exactly the same thing as a generator, just the opposite way, right? It takes the electricity, makes it into a rotational magnetic field, which spins the rotor, which gives the power on the other, gives the spin and mechanical energy on the other end. So flux is extremely important because it's across all of the disciplines, right? Anything that you have to design, right? Which is why it's important also in the alternative energy research and pretty much everything else. You will see flux, 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 flux all the time. Now, as I said, if you have some kind of closed curve, it doesn't have to be a perfect circle. We are talking about, again, oriented curve C. We are going to have tangent vector T, which is measuring the tangent vector T. I'll move this C. It's the worst possible place where I could put C. There we go. C. Then we have vector N, the normal vector. Guys, those two vectors are your 11.9, right? And now, perpendicular to those two vectors, in the K direction, where K is the T cross N, flux goes that way. So flux across the closed curve. It closes off an area inside. So all of the stuff going up, right, from this thing. And it's defined by the bound or the edge. Now, for us to work this out, we have definition. It says, let vector field F be F and G, be a continuous vector field on a region R of R2. Let C, curve C, be given by that parameterization R of t, which is good old x of t, y of t. We just had the example with the sine and cosine unit circle, where A is less than t less than b. B, a smooth oriented curve in R that, and this is very important, does not intersect itself. Number 8 or infinity, not good. It does not intersect itself. So 0 good, 8 no good. The flux of the vector field F across C is F dotted with the normal vector, the S, and then when you work it out, you get f of t, y prime of t, minus g of t, x prime of t, dt. There you go.
So with the integral with the c, would that also have the stupid circle thing?
Yeah.
So that literally just means that it's like, okay.
It's just mathematical notation. That's all it is. Do you have to write it? No. You don't. Right? It's just, I don't know, maybe integral looks cooler with it. But that's all it is. Now, I did talk about importance of where you're facing the fan, right? So you have the notion of the outward flux. And the outward flux is the one on which side of the picture it is coming out of. Because we're talking about the area, right? As soon as you close a loop in space, you have a plane that the loop closed and there is in front and behind, right? So for the counterclockwise orientation of C, which is, you know, word oriented, it's not there for decoration or annoyance of spelling. It is there because you need to have orientation. In the case of the unit circle, orientation is counterclockwise. The outward flux would be the one where you feel the stuff as you stand in front of it, right? So over here we would say if C is a closed curve with a counterclockwise orientation, N is the outward normal vector, and the flux integral gives the outward flux across C. So all of that falls in a place, but you have to make sure that you have the counterclockwise. Now, I'm not sure if you know that if you spin the fan the other way, what happens? Yes, the airflow goes the other way, right? It's very inefficient. It's very little, but you're not going to get the same side of the fan give you the, right? So only if you spin the right way, and that is the oriented part of the word oriented, so spins the right way, then you get outward flux, which is you will feel the wind push into you out of the fan, right? That's that part. Now, with the flux, are we expecting rotational field to give us a value? No, right? Because for flux, please don't think about rotating blade when you're thinking of the fan. You don't even see the blade. It's spinning so fast. There is, right? You know, because, right, you're smart. You've seen the fan. You know the principle on which the fan works. I can't have you now focusing on spin of the blade. That's not important. What's important is the face. It's much better to think of this as fan, right? And the stuff coming out of it. That's the way you think of flux. Not of the spin. That's circulation. So, when you are looking at the flux, it's just how much stuff is coming out. So radial fields, ones that are radiating stuff out, fan is radiating wind out, right? Those types that radiate things are going to be, so pure magnetic field, right? That's going to have flux, obviously, right? Electric field and all of that. When you go out of your way to make them rotational, which you can, sure, then they're going to have circulation and other stuff. But if you just take a little fridge magnet and you look at it, there's no circulation to it. It's not producing rotational magnetic field. It's producing radial magnetic field, right? The magnetic field that it's radiating out of the magnet. So flux, not circulation. So for the fan, forget about the blade. Don't think about rotation of the blade. You are thinking what's happening with air molecule, air particles, right? And they are being radiated out of the device. I don't care which device, what is the principle on which device works. I'm just wondering what's happening with the air molecules. And they're being pushed out, so that's flux. They don't rotate. Now, can you make it into rotational? Sure. We just have to figure out how to make, how to make tornado, right? That's nature is pretty good at it, apparently. You've seen images, right? So, radial. It's so difficult to use this pen now. Radial vector field. F of x, y. This is a radial one that shines the stuff out. We are expecting to have a value here. We are again going to be on unit circle, which is r of t, which would be cosine t sine t. And immediately r prime, because we are going to need that. That's where your x and y prime are. Negative sine t cosine t. So we have our, we know that t is stuck between 0 and 2 pi for the full circle. Remember that the curve has to be closed. Can you have less than a full circle? The answer is yes. It's just going to be closed across. I can just have half of the circle and then I have to close it across. It's still closed. How smooth is this? Okay. So you have to be very careful, right, with these kind of things. All right, come on. So we go with integral 0 to 2 pi. F. So guys, these are my F and G. These are my X and Y, and this is my X prime and Y prime. If it helps with the colors, do the map so that you can follow the formula, which we'll talk about again. So now what I have here is my F, that's cosine X, times another cosine X for Y prime, minus Y, which is sine, no, these are not cos, these are t's. Cosine t and cosine t and sine t, there we go. And X prime is the negative sine t, dt, and immediately, again, equals to 2 pi, right? Cosine times cosine is cosine squared, negative sine times negative sine is positive sine squared plus cosine squared is 1, and then integral of 1 dt is t, 2 pi minus 0 is 2 pi. So we see that the radial field, right? So sun, pro-dimensional, right, radiates its radiation energy, right, which is X-ray and ultraviolet and all the other radiation things. It's not radiating heat, right? If you park 1,000 miles away from the sun, do you get burned? You don't, right? Heat doesn't transfer to vacuum. So sun is 10.4 million degrees, right? We have fusion reactors where we have on the planet 150 million degrees. So we make devices that are 15 times hotter than the sun in science labs. And the planet didn't melt, all right? Nothing melts. So it's radiation that hits our atmosphere and then heats it up, and then we experience heat from the sun. So sun being closer or further away has nothing to do with our seasons and things like that. It's the angle at which you heat the atmosphere over the period of time that makes summer, not how close these are. Anyway, talking about the radial field of the sun, it's going to radiate energy in all directions. It's the circumference of the planet, right? And how big the planet is, or how much radiation is going to hit the atmosphere to heat the planet. So we understand radial, and we see that we are getting stuff because that's not zero. Now for rotational vector field, we better get 0 in the calculation. So rotational example. Our vector field is negative y x, and our r is still cosine t sine t. Our r prime, which we need, is negative sine t cosine t, and we take, the pen is cutting out constantly. So now integral 0 to 2, we have our negative y, that's negative sine t, then x is a cosine t. Sorry, we need f, which is negative sine t times x prime. Times y prime, sorry. Cosine t. There we go. Minus x, which is cosine t, times negative sine t. There we go, much better. dt. See, not brackets. There we go. Equal to integral of 0 dt, which gives us 0 on the other end. Ta-da! So these are extreme examples, and you have everything in between.
This on the test on Friday?
Which is in 2 days. The answer is no, unless you want it. Nah?
Thanks for this.
This is far easier and cheaper than anything in chapter 13, like even 13.1.
Yeah, I just need to go into this.
That's what Calc3 is all about. Great. Bye.